I'm sorry. So you said that the box can't, I'm sorry, let me back up. What's the mass of the box?
30 kilograms.
30 kilograms. And the angle of the ramp is something that we can change, so we don't know the angle of the ramp. But we know the cable can't exceed 200 newtons. Look, the first thing you should have done is said that T has to be less than or equal to 200. That's how you phrase something mathematically that represents something you saw on the paper. And if you didn't know that, write a note to yourself. This is a threshold problem, and we'll have lots of threshold problems this year. So when you have a threshold problem, that means there's something that can't be exceeded in the problem. When that happens, you need to figure out how to deal with an inequality. Otherwise, you don't know whether something has to increase or decrease in order to get to the threshold. So, big banner in your notes, big banner near your homework, threshold problems require an inequality. They require it. And your job should be to preserve the inequality. You're going to hear me say that phrase a lot. And I use it in all of my classes. Your job is to preserve the inequality, which means at the very end of this problem, there should be an inequality in your answer. This is way different than a lot of the stuff you've done in other classes. And I understand that. But yesterday I was working with a student after school, and it was clear that they're jumping at answers. You can't jump at these answers. Have you figured that out yet? You've got to go through a process. There are ways to skip forwards in this process. But if you're not familiar with them, you've got to do the whole process. And I see a lot in this class more than my second period. So I talk about you guys in second period. I say that you're too quiet, you don't ask enough questions, and I often feel like you're not doing any of the work really. You're just kind of looking at me and nodding. So that's the thing I say about you in my other classes. I talk about you all the time. That's okay. They're overzealous and they're boisterous, but I'll be honest with you, they ask questions. They don't let me get away with stuff. You guys are just hoping the bell will ring. Now, I'm going to go through this problem, but this is exactly like every other problem in the inclined plane homework. And I'm under the impression right now that I could say, take out a clean sheet of paper, name it up right-hand corner, and give you an inclined plane pop quiz. And you guys will all deal with it expertly, because only one of you in the last week has asked me any questions about the inclined plane problems. So I was surprised. So that suggests to me, you guys have done something none of my students have ever done. They've mastered this on the first attempt. I'm ready for a test Friday to make sure of that. So, I'm going to start with a free body diagram, and I could skip through a lot of these problems because I know how to do them. If you can't skip through these steps, then you should have all of these steps down for this problem. I have been amazed at the number of students who, when I asked, how do you draw the normal force, have been unable to draw the normal force. That they don't realize it's perpendicular to the ramp. Like they don't know what perpendicular to the ramp means. If that's you, you should be stopping me right now and saying, I don't know what you're talking about. Okay. Perfect. That means you all must be excellent. We will know soon. I believe this is a net force equals 0 problem. Right? We want the box to stay there. If it's accelerating, the string broke. So, is there anybody in this room who doesn't doubt that as I increase the angle, the string has to hold on tighter and tighter and tighter? Does that make reasonable sense? So, I expect at the very end of this, I'll have a relationship that shows me that as I make the angle bigger, the tension in the string must be getting greater. I need a coordinate system to align with this. Since there's no acceleration, it really doesn't matter how I do this. So I'm going to choose to do it to align it with as many forces as possible. But I would have aligned it like this anyways. It's an inclined plane, and aligning it with the plane makes the most sense. One of the hardest parts you guys generally have with that is knowing that the angle goes here. You have to figure out where that angle goes. It goes with the place that's between where the normal force and the weight are. So just follow the normal force down, and the angle goes between the normal force and the weight. That's how you figure out where the angle goes. So if you line the y-axis up with the normal force, just trace the normal force down, and the angle goes between the normal force and the weight. Every time. Every time. That's how you do it. So if you didn't do this before, you're putting it in the wrong spot, and trust me, I know when you put it in the wrong spot because you screw up your sine and cosine. You're easy to pick out. You're not going to hide from me. I'm looking for that mistake. I put that mistake in the multiple choice. So if I were you and you just found that out, write that down. Just make sure the y-axis is aligned with the normal force and trace the normal force down and stop playing with the weights in the back because they're not involved in this problem at all. Yes, sir. My next step is to break up the weight into a set of components. These components should be aligned with the x direction and the y direction. So this one right here, this one I'm kind of reinforcing, that's the component that's in the y direction. And this component right here is the component that's in the x direction. So mg sine theta, mg cosine theta. Questions? All right. Net force equals 0. So net force in the x direction, net force in the y direction equals 0. I'm going to look in the x direction, say mg sine theta minus tension equals 0, and normal minus mg cosine theta equals 0. Does that make sense? Any questions? All right. At this point, this problem is pretty well done. We have done all the physics portion, really, to this point, meaning we've done what the set of steps that I gave you for Newton's laws will give you. It'll give you two relationships that may be able to be used to solve your problem. So that's what all of this leads to. By the end, two relationships. You may have more, but this will produce two. One for the net force in the x and one for the net force in the y. Now, how you use those matters. My recommendation on a problem where you have an inequality is to substitute into the inequality. That is my recommendation. When you have a problem with an inequality, substitute into the inequality, meaning this is my inequality. It says T is less than equal to 200 newtons. So I'm going to solve this relationship for T because I know T equals mg sine theta. Since this is an equals, I will sub that into the inequality, which will give me mg sine theta, which is less than equal to 200. That's me substituting into the inequality. That preserves the inequality. Any question about that? Yeah?
So you made the left side going positive for this question?
Yes. All right, so all that's left is to solve this for theta. We know that m was 30, we know that g is 10, so this is 300 sine theta is less than equal to 200. And this is why I think it's important to preserve the inequality. At the end, we have an inequality as our answer, telling me very clearly what my answer is, right? I could solve this for theta. I could take the inverse sine of both sides. But it tells me clearly whether the angle has to be bigger than this in order to maintain this problem or less than this to maintain this problem. Trust me, right now, this one's easy. You know that if you make the angle bigger, you expect the tension to get greater. There will be problems where that will be less so, where it becomes more obscure. And so I encourage you to always substitute into the inequality when you can. And that way you know whether the thing you're looking for must be bigger than some value or smaller than some value. Told us about a force, the tension. In this problem, this is problem number 7, we have a whole bunch of motion equation information. Like we're looking for initial velocity. We're told the final velocity will be 0 after the car has traversed a distance of 1.5 meters. Those things are all true. We don't know how long it's going to take for the car to get there, and we don't know what acceleration the car will experience, but we want to know how fast the car was pushed. If I had one of these two things, I could figure out the initial velocity. If I have one of those two things. Looking at the picture, it's an inclined plane problem, which suggests I could use forces on it. So what would force be able to tell us that we could use for our problem involving motion equations? Yes, sir. Acceleration. Because, and I have said this before, the only thing force can really do is tell us about a force or an acceleration. That's all it can do. In the last problem, we could use it to tell us about the acceleration. So that's what we're going to do. We're going to use it to talk about the acceleration. I'm going to start with the free body diagram, but this is the exact same problem we just did without the tension. So I'm not going to spend a lot of time needling out the free body diagram. In fact, my expectation, because you guys asked nothing about the free body diagram before, is that you guys are already done. You know exactly what I'm going to write here. And I know that's not true, and I know you're just waiting for me to prove it on a quiz, but at this point, you won't ask questions, and I don't feel compelled to try and anticipate the questions, because perhaps I'm wrong. That's what I get when I work out my free body diagram. It's the same every time when it comes to inclined plane. Are there any questions about any of the decisions I've made? I'm making this direction the positive x direction. I've kind of suggested before that you should always make the positive direction the direction of your acceleration. And I'm going to do that here as well. Yeah?
Why did you choose to line up the normal force, the y? Why would you line up the normal instead of the 8? Is there any particular reason?
Yeah, actually. When we talk about lining up our coordinate system, I gave you two priorities. Now, this is not a why, this is just a what you should do. I said line it up with the direction of the acceleration. I think the car is going to accelerate down the ramp. Right? If I put it at the top, it would accelerate down the ramp. If I try to push it up, it's going to slow down and stop and go back down the ramp. So I'm pretty sure the acceleration is this way, which is why I want you to put the acceleration. But that doesn't tell you why. So let me explain why. Eventually, we only do one-dimensional problems. So eventually, we're going to break the problem up into a net force in the x and a net force in the y direction. If I line up the coordinate system with the weight, that means I'm lining up the x direction this way, right? But my car then is accelerating both that way and that way because it's going down the ramp, right? So I would have to set this equal to ma in the x direction and ma in the y direction, and that produces a much more challenging question for us to solve. So if we can line up our acceleration with one of our cardinal directions, then one of these becomes ma and the other one becomes 0. And we know that anytime you have a 0, that's better. So, all right, so we're kind of done here. This is mg sine 30 equals ma, and this is normal minus mg cosine theta equals 0. Don't really care about the y direction. I care about the x direction because that has the acceleration. And it looks like the acceleration is 5 meters per second squared. Sine of 30 is a half, g is 10, and the mass cancels out. I could do the math. Do you need me to? Yes, please. Okie doke. Let me get this out of here. So step number 1, divide by m, assuming it's not 0. So g sine 30 equals a. G is assumed to be the acceleration of gravity, that is 10 meters per second squared. Sine of 30 is 0.5, so A is 5 meters per second squared. Yep. So when I chose to draw my arrow downwards right here to make that gravity, I indicated a direction already on my free body diagram. Now, I made this direction positive, which is why mg sine theta is positive. But when I had net force in the y direction equals 0, I said normal minus mg cosine theta equals 0. This negative sign indicates that this component of the weight was downwards. But, and I'll remind you of this because this part's important, and I get this question a lot, and it's something I told you about even weeks ago. G isn't negative. Downwards is whatever you call it to be, positive or negative, depending on the way you use your problem. I am taking care of direction early in this problem. When I draw the arrows on the free body diagram, I am indicating direction. And when I assign positive and negative to the x and y direction, I am also dealing with direction then. So that I don't have to have some blind plugging in of a negative number. You don't want to plug in negative numbers blindly. They will generally, in most cases, screw up your work. So you'll notice I'm very specific about what's positive and negative, but I would never put in a negative 9.8 or a negative 10 blindly in for G. G is just a value. Gravity has direction. Yes, sir?
When you set up the coordinate plane and you assign positive and a negative direction, that doesn't mean that the numbers themselves are positive and negative. It just means one's less than the other, correct?
No. It means positive and negative. It means direction. It does not mean less than another. It specifically does not mean less than another. I mean, when I assign the directions to the coordinate plane, I'm trying to make sure that in my one-dimensional problem, I recognize that one of these arrows is in one direction and the other one is in the opposite direction. And so my positive and negative that I assigned here is to indicate that. Add up the forces taking into account their direction and set them equal to 0. Does that make sense? Okay. Because I'm about to screw with direction again, so I need to make sure we're all on board with this. Can I keep going? All right. The acceleration is 5 meters per second squared, but I've indicated down the ramp is positive. But the car is going up the ramp. So to be consistent and apply direction correctly, I have to make my 1.5 negative, or I have to reassess direction right here. But I made down the ramp positive, the car is being pushed up the ramp, so its displacement needs to be made negative. You have to be consistent. You can change it between the Newton's law portion and the kinematics portion. But during a step, you have to be consistent. I'm just going to stay consistent for the whole problem. All right, I've done all those things, so all that's left is a kinematics problem. I'll throw out time and do v final squared minus v initial squared equals 2a delta x. Pick one of your motion equations that has everything in it but time. This is the one I'm going to use. And 0 squared minus v initial squared equals 2 times 5 times negative 1.5. 15 over here. It's negative and negative vi squared. So vi is going to be plus or minus the square root of 15. Now, I'm being careful here. Plus or minus, which one is it? Technically, it's minus. Up the ramp, right? We have to push the car up the ramp for it to go up the ramp, and negative is up the ramp. But I would put my answer as, whatever, 3.9 meters per second up the ramp. There's a person pushing on the box. That's the takeaway. So I'm going to do this problem in a manner that will solve both problems. I'm kind of going to do this fast because I know I'm short on time. But same kind of thing, except this time, just to save a little bit of my sanity, I'm just cutting out the middleman of dealing with it. We've done this exact same problem twice already. So the first problem is a net force equals 0 problem. So normal minus mg cosine, is it 25? Equals 0. And applied force minus mg sine 25 equals 0. So the applied force equals mg sine 25. That's part A. That's how hard I have to push for the box to go up the ramp at a constant velocity. Net force has to be 0. However, the problem changes halfway through, and we then change to where the force of the box, the force on the box is accelerating the box. Well, the only thing that's going to change is that now it accelerates up the ramp, but I've already set up my coordinate system in such a way that they're lined up with the x direction. So now I'm just going to say the applied force minus mg sine theta has to equal ma. So now my applied force has to be ma plus mg sine theta. I have to push harder to get it to accelerate? Makes sense. How much harder? This much harder. You can throw the numbers in there and get your numerical answers. I don't care about them. Now we've done it for every problem where somebody's pushing a box up a ramp. And number 5?
For number 5,
Aww. The real question is probably, why is real life different than this? There's a number of ways to answer that. So let's first deal with the fact that, although some of you did this, I know that there's the people who are too scared to ask the question, who really need to ask that question, who won't. Meaning they don't know why this is true. They don't understand the question. And they don't have the courage or charisma to ask it, which is too bad. But Mr. Shelton is that person. He's rough. So, person. Sliding down water slide. It is inclined, I don't care. And we want to see whether a 20 kilogram or a 10 kilogram person. These are pretty small people, by the way.
yeah.
You'd be chucking babies down it. And 10 kilograms about 20 pounds. 20 kilograms about 40 pounds. So 2.2 pounds per kilogram. But free body diagram. And I'm probably only going to do 1 or 2 very complete free body diagrams today, because at this point, I can't convince you to do them right, even if you're really trying. I had somebody at my desk yesterday who had no idea what I was asking when I said, why don't you draw a free body diagram for this arrangement? And I had to step them through every single arrow. That's the only people that are left in my estimation, the ones who never knew what we were doing. The rest of you should have a clear idea. So I drew the first arrow. What does it represent? All right. Don't say gravity from now on, please. Please say weight. Weight is the force of gravity that acts on something. I would say, I wouldn't care or be particular, but we just saw what happens when we're not particular. Right? It took a long time to get weight equals mg out of somebody. So let's say weight. So we are very clear. That is the force of gravity that acts downwards. They're in contact with the ramp. This is the one where I've had the most difficulty with folks in the last couple of days. Perpendicular to the ramp. I guess I didn't understand how many people don't know what the word perpendicular means. But I drew this with the intention of it looking like a right angle. Does it look like a right angle? Yes. So with that in mind, perpendicular to the ramp is one of these two. Option 1 or option 2. Now I'm saying this knowing that the people who don't understand what perpendicular to the ramp means don't know why I drew this arrow at all. They're in trouble. And they're going to continue. They will not be able to pass this quarter. You need to fix the problem. Get it fixed. However, the rest of you who do know why I drew it this way understand that I'm going to draw arrow number 1, not arrow number 2. Right? It's the one that pushes away from the ramp. I doubt the ramp is shoving them under. No. So, All right, so these are the only two forces acting on our person. I'm going to draw a coordinate system that could be used to determine which forces go in which direction. That coordinate system is going to be aligned with the likely direction of the acceleration, which I will call the positive x direction. And I'm going to put the, and I will put this as the y direction. Now, yes? So if we want there to be a frictional force, what direction do I draw the frictional arrow? Okay. Now, I have said this out loud more than once. If you have heard it, good. If you haven't, well, hear it now. Friction is a percentage of the normal force. Have you heard that phrase? I know I've said it. Friction is a percentage of the normal force. It has to do with the two surfaces in contact. Can we assume both swimmers will have the same percentage? I think we can. Skin on the water or their bathing suit on the water. Very likely to be the same percentage. So now they're not going to have the same normal force, but the same percentage. Everybody follow along?
Yes.
I'm going to use a symbol for percentage. I'm just going to use the percent symbol to indicate the percentage. So friction equals a percent of normal force. Good so far? All righty. So we've made this problem a little more complicated than intended by including a frictional force. If you don't want to do it this way, then don't include the frictional force in your analysis and do the analysis your way without the frictional force. It'll be the same. We know the person accelerates because they are making it to the bottom of the slide, and therefore, starting from rest, they would have to accelerate down the ramp. I'm going to make the positive x direction the direction of the acceleration. I notice that my free body diagram has one force that is not aligned with the axes. I will have to take that force and break it up into its components. To do so, I need to know where theta goes, and theta goes here. If you don't know why that is true, then it's not in your notes correctly. Let's get it in your notes correctly. Theta goes there for a number of reasons that can be proven to you using triangles and geometry. But I will just tell you the best way to figure it out without any of that is to trace the normal force back down onto the other side, and the angle is where the normal force and the weight are. So just trace the normal force across the other side and place the angle between that and the weight. That's how you do it. Yes, ma'am. Unless a problem specifically brings up drag, you wouldn't use it in your calculation. Okay? Now, that might be the reason why one person makes it down first and the other one doesn't. But I wouldn't include it in your calculation. I don't think you know how. So there are two components that will act on the person. This is taking the weight and breaking it up into its two components. These components will replace the original force that is there. So in this direction, I will have mg sine theta. And in this direction, I will have mg cosine theta. I've talked about why these are cosine and sine and why they go the way they do a couple of times. Do you need me to do more than this? Because I don't want to, but I will. Okay, so once I've done this, I can take this and break it up into its components. And when I do, I will get net force in the x direction equals ma, and that will be mg sine theta minus friction equals ma. And in the y direction, I will have net force minus mg cosine theta equals 0. We lined the x direction up with the acceleration purposefully, so the y direction would be lined up in such a way that its net force would equal 0. That's why we do it this way. Now, it seems to me that if we wanted to be able to show whether the light person or the heavy person have a different acceleration, we would have to do something to this relationship. Now, you guys all want to drop, the masses and G and all that in there, and I don't. I'm going to do this different than you would. I know that numbers have been given. I want to prove that the numbers don't matter. To do that, I'm going to do algebra. First, let's consider this for just a minute. Friction is a percentage of the normal force. Well, the normal force equals mg cosine theta. So the friction equals some percentage times mg cosine theta. That's just pure substitution. Now, this part might be hard for you because you guys are sometimes challenged by this. Do we understand that the percentage that I've written there is just a number between 0 and 1? Is everybody okay with that? It's a fraction. I don't know what that fraction is, but it's just a number between 0 and 1. I can treat it like any number. If you want, I could put a symbol there, like a lowercase c or something. But I'm just leaving a percentage there because we do have a symbol that stands for this. I'm saying that because it seems to me that I could replace friction with percentage mg cosine theta equals ma by taking this and doing substitution. I'm just doing substitution. I'm doing algebra. Nothing fancy. I know it looks like alphabet soup, but this is what we have. And now I want to prove something to you. M is what? What does it represent in this relationship? It is the mass of the writer. It's a non-zero number, correct? If it's a non-zero number, then I can factor it out and divide it out on both sides. Suggesting that the acceleration does not depend in any way on the mass of the rider. If it did, they would ask you your mass before you got on the ride, because you might accelerate too fast. And notice, it doesn't matter whether friction's involved or not. The frictional force comes from the normal force, which also comes from your mass. So unless you wear an ultra sticky swimsuit, you're both going to slide down the same. What might cause one rider to accelerate more than another? Probably how much surface area they have. That's the number one thing that would cause a distraction. If you sit up in the water slide and you act like a big sail, you'll probably make it harder to go through the wind than if you lay down and make it so that you pass through the water without being a big sail. You'll probably go faster. Either kid could slow themselves down just by sitting up. Most of you who have been on water slides are well aware of ways you can make yourself go faster. You figured them out. All right, that's number 5. This is not a particularly, unique example here. That we produced something that told us about the acceleration and used information in the problem, a unique equation defined by the situation of our problem. Let's talk about no friction codes. Because some of them are more ambiguous than others. I will not be ambiguous on a test. I have no trouble being ambiguous on homework, right? Homework is just that, practice. You should be asking questions. But you'll have a practice test Wednesday, and you'll see what I mean by I will not be ambiguous. I will state clearly whether friction is involved in a problem or not, so that you will not be surprised. And you can probably assume that I have in mind whether I want you to use friction or not ahead of time. So, no friction, icy surface. Smooth surface. No resistance. Slippery surface. These are all code words to suggest there's no friction. Now, again, in a testing environment or on the AP exam, they're not going to try and put you in a situation where you have to figure out if there is friction. The only way they would do that is if they gave you a situation in which you had enough information to figure out the size of a frictional force based on the acceleration. An example of that would be this. And I'm making this bonehead simple so you don't have to downshift into your calculators to figure something out. If I have a 10 kilogram mass and I'm pulling on it with 100 newtons of force, I have an anticipated acceleration of 10. Does everybody see why that has to be true? Net force equals ma. So under these circumstances, if the only thing I'm doing is pulling on it with 100 Newton force, then 100 equals 10 times a. I think the acceleration is 10. You do this and measure the acceleration to be 7 meters per second squared. You might have to figure out that, well, something's wrong then. What is pulling on the box this way? What is a likely candidate? Friction would be a likely candidate in this circumstance. Do I have to tell you there's friction? No, but if I give you that the acceleration is 7, and we would expect it to be 10, if this was the only force there, then yeah, you might have to figure out that there's a frictional force. But under no other circumstance will I be doing anything like that. And the only way that would ever even show up is likely multiple choice. I am not writing problems like this, not yet. I'll wait to the end when you have accumulated enough information where you can make a more reasonable calculation. All right, anything else on the homework that you would like me to speak to? True again.
Attached to the box in order to keep it from sliding down the ramp. There is no friction on the ramp. If you unload the ramp, you change.
Got it. 200 newtons is the maximum amount of force that the rope can withstand before breaking, and the box has a mass of 30 kilograms. Is that right? Okay. This is a threshold problem, and I worked it out in first period as well, and it's appropriate that we talk about it because threshold problems on their own merit require a different way of thinking. Let me first start out by saying you need to be able to write out what a threshold is. There's a mathematical way to write out thresholds. You've been trained in it for years, but you would never associate this word with a threshold. So the best word to use here, inequality. The tension in the rope must be less than or equal to 200 newtons. This is our threshold, and it produces an inequality. At the end of this problem, your answer should be an inequality. It should tell you whether the angle has to be less than or greater than some value. It's important to preserve the inequality. You will hear me say this a lot because oftentimes we end up going through several transitions and several algebra substitutions. And in the end of the day, we might have something that largely looks different than what was started with. I think here, in this problem, we're going to have something at the very end that probably has something to do with the angle and whether the angle should be bigger than a number or less than a number. Now, this one's pretty straightforward, but it's a good example of how to preserve the inequality. And I want to demonstrate how you do that because it's going to come up a lot. First, is there anybody in the room who really is concerned about whether making the angle bigger will increase the tension or decrease the tension? I mean, do you know the answer to that? Let me say that again because I might have stumbled a bit. But I have a situation in which I can increase or decrease the angle. Does this look like the problem to you?
Yeah.
If I'm holding on a string and I increase the angle, do I think the tension is going to increase or do I think the tension is going to decrease?
Increase.
So I think we have a bit of a understanding of our expectations in this problem. But I want to be clear, at the end of the day, you may have a more complicated situation where you don't know how changing one thing affects the others. I promise you, our very next subject, when we do uniform circular motion, there will be some unusual results. So preserving the inequality is important to me. In your notes, I would even put that in the table of contents. How do you preserve the inequality? Because I'm going to describe it. First, this problem still is a Newton's law problem in that net force is going to be equal to 0. I do not want the box to slide down the ramp. And based on our conversation so far, I think I can kind of spirit through this a little bit because I know the forces acting on the box are not much different in this problem than the other problems we've seen so far. There's going to be one like that. There's going to be one like that. There's going to be one like that. Tension, normal, and weight. Net force is going to be 0, which means I can make my coordinate system go any direction I'd like. But I think that all of you would probably agree that the best choice here is one aligned with the two forces that are at a right angle to each other, which means aligning them with the ramp. So that's what I shall do. I've aligned my two axes to be aligned with the ramp. I'm going to make this direction the positive x direction and this direction the positive y direction. I've already done this many times, but I'll say again, this is theta. It is the angle that exists between extending the normal force onto the other side and the weight. I believe there are two components to the weight that I'm going to use in this problem. So I'm going to break up my weight into its components. And I have done this now, 3 times in this class alone? If you have not asked questions by the 3rd time, I assume you know how to do this. And I notice that this is the opposite side, so it will be mg sine theta. And this is the adjacent side, it will be mg cosine theta. Moving forward, net force equals 0. So net force in the x direction must sum to be equal to 0. And net force in the y direction must sum to be equal to 0. This force and this force are in the y direction. One points up, one points down, so normal minus mg cosine theta equals 0. This force and this force are in the x direction. One goes down the ramp, one goes up the ramp. So mg sine theta minus tension equals 0. I'm just repeating all of my steps. So when you guys come and get help and I start going through the steps and you're not using them, you'll know that I could say to you and be all smug about it, I follow the steps every single time. And I'll be all smug because that's how I like Mr. Shelton. Smug Shelton. Now, here's where things get a little bit more interesting. Not very interesting, a little more interesting. I want to know what will the angle be where the string will break. What angle do I have to keep it beneath? And here's where I add something that you didn't know. This is how you preserve the inequality. When you have an inequality to use, your job is to preserve it. What that means is you substitute into the inequality. To preserve the inequality, to know where the inequality is in your problem, you substitute into the inequality, which means I'm going to solve for t. I'm going to say t equals mg sine theta. And I'm going to substitute into my inequality so I can preserve the direction of the inequality. That means mg sine theta must be less than or equal to 200. All right, so we're pretty close to the end. We're trying to find out what angle where it breaks, but we have something better here. And this is what I really want to be throwing out there in front of you. mg is 300 because it was 30 kilograms and g is 10. So sine theta must be less than or equal to 2/3. The reason why I want to do it this way is it preserves the inequality. It tells me whether the angle has to be bigger than a number or smaller than a number. If you had just substituted 200 in for t, you would have lost the inequality. This way, it stays preserved in the problem.